Thanks, Yuqing. Thanks for the introduction. It's a great pleasure to be here today. So I would like to talk about learning multi-item auctions today. And I would like to share with you a new modular approach that achieves learnability through a new concept of robustness. This is joint work with my student Johannes Brussel, who just finished his master's degree from McGill and moving to LSE to complete his PhD, and also with Kostas Daskalakis. And I want to point out that if you have questions, feel free to interrupt me. And I think it's better to have a more interactive talk than just having myself speaking for an hour. All right, so let's start. So the question that I'm interested in is how can I design an auction to maximize the revenue? And maybe I'm selling one item, maybe I'm selling multiple items. But even in the simple setting, when there's only one item, the bidders, they have private values about this item. If I have no idea what these values are, this is not even a well-formulated problem. So to make the problem analyzable, we often make the following assumption, that is, me as the seller actually knows the distribution F from which the values are drawn from. And this assumption is super crucial. And with this assumption, we can have an analytical approach to the problem. And in fact, Myerson in the early 80s showed that under this assumption, you can actually characterize the optimal single item mechanism if you assume the bidders have independent values. And this will be the setting that we're in today, meaning the bidders have independent values. Later, I'll move on to talk about multi-item auctions. There, I'll make a distinction when the items have independent values or correlated values. Okay, but just for this talk, just remember the bidders are always independent. Okay. Okay, so Myerson's result is can arguably be said being the workhorse in theory and auction in both theory and practice for auctions. So if you're serious about applying this type of theoretical result in practice, one question you will ask is, okay, so where do I get these priors? So, and the common answer people give is that, okay, you can either get it from market research or maybe from observation of bidder behavior for selling similar items in previous auctions. But if we really take this answer, then it means that in reality, we don't really know F. Right? For example, maybe you have seen an auction for selling some type of item 100 times. And the bidder's value is drawn from a Gaussian. So you have 100 samples from the Gaussian distribution, which I plotted out here. So it looks kind of like a Gaussian, but it's not really a Gaussian. Okay. And now the question is, you only have access to these samples. And how do you use these samples to design a good auction? All right, so, and this has been formalized as sample-based mechanism design. And here you weaken the Bayesian assumption by saying that I don't know exactly the distribution, but I can draw samples from it. And the question is, can I still learn a good mechanism, either approximately optimal or up to epsilon optimal, using only sample access to the distribution? Okay, so when I say approximately optimal, I mean you get a constant factor approximation of the optimal revenue. When I say up to epsilon, I mean you're getting almost all the revenue with a small additive epsilon error. Okay, so that's the goal for sample-based mechanism design. And the game here is how many samples do you need in order to get a mechanism with certain performance guarantee? Okay, so that's what sample-based mechanism design is about. And in the single item setting, I mentioned earlier that Myerson already provides a characterization of the optimal auction. And in fact, the characterization shows the optimal auction is quite simple. So thanks to this sort of simplicity in the optimal solution, we understand the sample complexity very well here. So we have almost matching upper and lower bounds required to get almost optimal revenue. Okay, so that's what happens in single item setting. So for today's talk, I would like to focus on the more complicated setting, namely you're selling multiple items as the seller. And probably many of you know that in multi-item auctions, first of all, Myerson's characterization fails. And it's not really an issue with Myerson's approach. In fact, no general characterizations, no. Even if you're only selling 2 items, okay? So Myerson shows that for 1 item, there's a simple solution. But even for the slightest generalization of the setting, when you're selling 2 items, we don't have a general characterization, okay? Despite decades of effort. So I'm just listing, some of the literature about this problem. And okay, so like there's no characterization, clearly that's gonna make the sample-based mechanism design problem much harder. But still there are some positive results known. But all these results make a technical assumption that is all the items are distributed independently. Okay, so on the first page, I said that all the bidders are independently distributed. Here, I'm making an extra assumption that the items are also distributed independently. Okay, so under this assumption, there are a few positive results known. So most of these results are obtained using a sort of general framework based on pack learning, which I'll explain in the next slide. So let me first tell you what kind of results are known. So the first line of results concerns simple mechanisms. So because the optimal solution is not known in the multi-item setting, a recent trend in research has been focusing on designing simple mechanisms, usually of the form of posted price mechanisms, and prove like these are good approximations in various settings. So what happened in these 2 papers is that they prove you can actually learn these simple mechanisms with polynomial many sample complexity in certain cases. So that's the first line of work. So you want to learn simple mechanisms. So the second line of work by Gonczewski and Weinberg, they said that let's forget about simplicity. Let's just try to get as much revenue as possible. Quite surprisingly, they show you can get up to epsilon optimal revenue under the item independence assumption if you're willing to accept approximately truthful mechanisms. Okay, so the mechanism is not going to be exactly truthful, but maybe epsilon truthful. And what they show is if you have more samples, you will have closer to optimal revenue, and also you will have a mechanism that's more and more truthful. Okay, so that's the second line of work that happened in this space. And I would like to point out that there is one result that does not fit into the pack learning framework, but that result deals with one particular mechanism, and it's not a general approach. Okay, so today I want to show you another general approach, and I will show you that you can actually use that approach to improve both lines of results. You can use that to improve learning simple mechanisms, and you can also use that to improve learning up to epsilon optimal mechanisms. Okay. All right, so let me briefly tell you what is the pack learning approach that has been quite successful. So pack learning is sort of very well known concept in learning theory, and usually you use that to learn functions. So here we're applying that to mechanism design. And roughly it goes as follows. So you first fix a class of mechanisms. Okay, you fix this class H. For example, you might want to consider second price auctions, and you also want to consider all sorts of reserve prices you want to add in the second price auction. So all these mechanisms form this family of mechanisms. So after you fix the class of mechanisms, you draw samples from the distribution. And then you say, let's try to find the mechanism in this family that has the best empirical performance. So in our setting, that means you find the mechanism in this family that has the highest revenue on the samples you draw, okay? And let's call that mechanism M hat. And what you hope to argue is that even though you only use the samples to identify M hat performance, in our case, the revenue under the true distribution F is almost as good as the best mechanism in this family H. Okay, so that's the hope. So really what you need to prove is this epsilon is small. Usually you want to argue this epsilon decays in the fast speed in terms of number of samples you draw, okay? So that's roughly the approach. And for this approach to be successful, meaning that getting meaningful learning results, you will need to pick this family H that satisfy the following two properties. And I'm calling these two properties can be roughly categorized based on the nature of these two properties. The first one is about mechanism design, okay? So what does it say? It says that, okay, even if you can get an epsilon that's very small, you're only guaranteed that your M hat is good compared to the best in H. But how do you know the best in H is good compared to the real optimal when you're not restricting your mechanism to lie in this family H, okay? So this is usually known as representation error in learning theory. So here you're dealing with mechanism. So you require knowledge of mechanism design to understand whether the best in H is actually comparable to unrestricted best, okay? And there is a second component that's about inference. That is, you want to argue that this epsilon, which I have here, decays in a fast speed in the number of samples. But notice that this epsilon is actually a function of the number of samples and the family of mechanisms, okay? So usually if you take a family that's too complicated, epsilon is not going to decay in a fast speed, okay? So let me be a bit more specific. So to apply the pack learning approach successfully, you really need to choose an H that satisfies both properties. And these two properties are kind of in conflict. So to satisfy the mechanism design property, you will likely to pick H to be quite rich, right? Because you want to compare to the unrestricted best. If you just have a very small family of mechanisms, likely this is not gonna give you good performance, okay? And then for the inference property, you actually don't want your family to be too complicated because that's gonna make your epsilon decay in a very slow speed, okay? Usually the way to bound the decay rate is by proving some kind of statistical complexity for your family of mechanisms H. There are various concepts, like for example, you can use VC dimension, you can use the pseudo dimension, you can use Rademacher complexity, but all these are sort of a way to say how complicated your family of mechanisms is, okay? So to get one, you want the family to be complicated, at least not too simple. For two, you don't want your family to be complicated. So to get the result to work, you really need to consider mechanism design component and the inference component jointly. Okay, so that's for the pack learning approach. So hopefully, okay, right. So that's for the pack learning approach. So now I would like to show you a new modular approach that decouples the inference and mechanism design component. Okay, and this approach has two steps. So in the first step, I want to prove a robustness theorem. I will give you the formal definition just in a minute or two. For now, just imagine the following scenario. So you're given an approximate distribution f hat, okay? All you know is that the true distribution is not too far away from f hat, okay? Suppose it's in epsilon statistical distance. And now what you need to do is you want to learn one mechanism based on f hat, okay? That's all you know anyways. So, and now you want to learn this mechanism such that it has good revenue for any possible true distribution F. So I'm calling this robustness because you want to learn a mechanism based on just one distribution F hat, but you want this mechanism to have good performance for every distribution that's in the epsilon ball around F hat. Okay, so that's why I call this robustness. And this is a theorem that only involves mechanisms. It has nothing to do with learning theory, it has nothing to do with this dimension and so on. Okay, so once you establish the robustness theorem, now I have the second step in the approach. That is, now you just need to learn F hat using samples from F. Okay, if you can learn an F hat that's close enough, I can apply my robustness theorem to get a learnability result for the auctions. Okay, and this part has nothing to do with mechanism. You don't even need to know anything about mechanism design to perform this step. Okay, so that's the modular approach. And in some sense, this approach provides a reduction that reduces the learnability of auctions to the learnability of distributions. Okay. And so what's the main like pros of this approach? I think the main pro is that with this reduction, we can now leverage all the tools and results from learning distributions, or sometimes known as density estimation from the statistics and machine learning literature. That's an area has been studied extensively for decades. Various results, various methods are known. For example, there's a recent trend in this area that talks about how you can learn a distribution to be close to the true one, even when your samples are corrupted or even truncated. So there are like very rich results in this domain. So now with this reduction, you can actually just directly plug in those results to get bounds for learning auctions. Okay. So one may wonder that, okay, so what you're saying is if you can learn your distribution with enough accuracy, you can get a mechanism with enough accuracy. Okay, that sounds trivially true. Okay, this is a valid concern and it's kind of correct, but the point here is how accurately do you need to learn your distribution so that you can guarantee that your mechanism has good performance? Does it need to be exponentially close, which is something very hard to do, or you only need to be polynomially close? Okay, and notice that we don't have a characterization of the optimal mechanism. For all we know that the optimal mechanism is very complicated and relies on details of the distribution. So it's not super clear how you can make such an argument. All right. Okay, so what I plan to do for the rest of the talk is I will show you the robustness results we prove, the model. And then I would like to apply this modular approach on two cases. So the first case I'm going to apply it to is how you can learn simple and approximately optimal mechanism under the item independence assumption. You will see that you can use this robustness-based approach to show learnability where the pack learning approach failed. Okay. And the second case I want to talk about is you can use this approach to learn up to epsilon optimal mechanisms. Remember that Gonzalski and Weinberg showed that you can learn up to epsilon optimal mechanisms for independent items. I will show you that you can use this approach to recover the result, but also go beyond independence assumption and learn the auctions in cases where the items are dependent.
Yeah. Can I ask a question? Let's make sure we understand it. So here, from what you write down here, your modular approach is just learn the distribution. So it's decoupled from mechanism design issue. So how do you take care of the mechanism design requirement here?
Right, so the mechanism design component is completely pushed into the robustness argument. So when you do the robustness, you have to understand mechanism design. you have to be careful to make sure your mechanism is incentive compatible and so on and so forth. It's just the learning part. Now you're only learning distributions. You're not directly learning the best mechanism. Does that make sense?
I understand what you are saying, but I still haven't figured out how it is related to the mechanism design, like a revenue optimization issue, for example.
Yeah, so the revenue optimization issue is take care in the robustness. Maybe like, I think when I show you the exact model, it will make more sense. So I will show you the exact model. So there, I think it will be clear to see. Like in the robustness, I would have a guarantee saying that this mechanism, even though you only use F hat to design it, it will need to have good performance, good revenue with respect to the true distribution F.
Okay.
So I push everything into the robustness.
Okay, we'll keep that in mind. And
yeah. So like I'll show that in 2 slides, and then yeah, we'll see if that makes more sense.
Okay, good.
Other questions?
No, not for now.
Okay, cool. Okay, let me move on. Okay, so now let me present the formal definition for the robustness. So what I want to point out is, okay, this is a crucial component in the modular approach I'm going to present. But also I think this is a sort of alternative, interesting alternative for sample access model. So if you want to learn distribution, this is a different type of model. I think, it's worth considering. Okay, so okay, to elaborate a bit more on that. So I want to basically discuss, why this sort of max-min model is at least an interesting alternative for sample access. So when do we actually have sample access to distribution? So this is sort of also another fundamental question we should ask when we do sample-based mechanism design. So sample access is a good approximation for reality if you say you have seen bids from previously run truthful auctions, okay? So in that case, you can say, okay, I'm going to use those bids as samples. But as we know that many auctions that happen frequently are not truthful auctions. Just think about a generalized second price auction Google is running every day. That's not a truthful auction, okay? So you see bids in a non-truthful auction. And what happens in practice is that you first take those bids and you invert the bid distribution to uncover the value distribution using some econometric methods, okay? But this procedure is not perfect. Some errors are going to creep into the procedure. So in the end, you will not have sample access to the true distribution. The best scenario is you will have an approximate value distribution, okay? But there's going to be some error there. And it's hard to pin down what that error is, okay? You only know there is some error, and maybe the error is not too big, okay? So that is sort of the motivating example for our model. So what is our robustness model? So we assume that for every bidder I, we're given an approximate distribution Fi hat. Now you can think about that as what the econometrician has provided you. You're given this Fi hat. And all you know is that the true world satisfy the following condition, that is the true distribution Fi and the one you're given Fi hat are close in some statistical distance, okay? And you can pick this D to be essentially most of the familiar statistical distance we care about. So in this talk, I'll talk about all sorts of the statistical distance, for example, the Kolmogorov distance, the Levy distance, the TV, Prokhorov distance, okay? So I'll talk about many of them. And what is your goal? Okay, your goal is you want to find a single mechanism M with access only to F hat, okay, only to the approximate distribution. But you want this mechanism M to have the following guarantee, okay? What guarantee? You want to say that for any possible true world that's close to F hat, this mechanism M has revenue, notice that I'm evaluating the revenue under the true distribution. Even though I don't know it, I'm evaluating the revenue under the true distribution. So your revenue, the mechanism should have good revenue, which reflects the true distribution. What do I mean by good revenue? I mean that its revenue is at least a constant factor of the optimal revenue for the true distribution minus a small additive term. Okay, that's the kind of guarantee I want. Only if the mechanism M satisfies this inequality, I say this is a robust mechanism. Okay, so the C is the approximation factor here. And we're writing C to be less equal to 1 because later you will see that actually sometimes I want C to be exactly 1. Okay. So a priori, it's not clear whether such a mechanism exists.
One moment.
Yeah.
What is the term after the C times optimal? It's minus polynomial something times H. What is H?
H is the, right, sorry. So H is the highest value you could possibly have for any item. So I'm assuming the distribution is the boundary range. Yeah, sorry, I didn't write down the notation here. So H is the highest possible value you could have for any single item. So it's not a purely multiplicative approximation. So I'm allowing to have some additive error as well.
So why this together this subtracted term is small?
Why is this small? Because if you make epsilon sufficiently small, you can make this small. So that's
it's not a thing here in this formula, right?
Sorry?
We cannot see it here. The polynomial something would be like
no, so the important thing, right? So okay. Yeah, so you have an epsilon there. So if you make epsilon sufficiently small, you can make this to go to 0. Yeah, so that's the point.
But the polynomial could add a constant, right?
Say it again.
It could be like epsilon plus m plus n plus 100.
No, right. So you're right. So I think the right way to write this, that was a typo, is epsilon times polynomial mn times h.
Okay.
Yeah, so that's the right notation. So it's epsilon times these two things.
What is
and you will see.
Yeah. What is m and n?
Yeah, m is, sorry, you're right. So m is the number of items. N is the number of bidders.
Okay.
Yeah, so you have something that's epsilon, which is how far away your distribution is, times a polynomial that depends on the number of items, the number of bidders, times the highest value. Okay, so if you normalize things, H is just 1. And so you're having an epsilon that's just epsilon times some poly mn. So that's the robustness guarantee I want.
So epsilon could be like polynomially large, small, like
right. So So for this to be meaningful, you would likely to choose epsilon be polynomial, small in the number of items and bidders. Yeah, and that's actually how you would use this robustness to get learnability.
Interesting.
Right. And it's important, the dependence, right? You're only having polynomial mn times epsilon. So that's going to give you polynomial sample complexity. If you have exponential in mn, then your sample complexity coming from this robustness will be exponential.
Okay. Yeah.
So that's the robustness model. And so here, there's no learning component. It's just about doing mechanism design in a sort of more adversarial setting. Okay, so of course, a priori, this is not even clear such a mechanism M exists. All right.
Yeah, one more question. What is
sure.
optimal Fi?
Yeah, so Fi is the true distribution.
Yeah.
So I'm saying your mechanism M should work for the true distribution, not the one you're given.
Optimal means optimal revenue?
Optimal revenue, yes, optimal revenue. So I'm only talking about revenue here.
So it's an arbitrary problem for the revenue or what?
Arbitrary problem? What do you mean?
don't have a problem. What is optimal something? It's
the optimal Bayesian incentive compatible mechanisms revenue. That's what I mean.
For any problem.
So you have M items, you have N bidders. So the input is just this product distribution, right? So that specifies your valuation. I'm looking for the optimal revenue with respect to that distribution.
Okay.
Yeah. So like this opt is really.
So everybody get one, or everybody can get several, or it's arbitrary?
That's up to you. Yeah, you can specify what kind of constraint you want. So for any type of this sort of constraints, this is the goal I want to achieve.
Okay, good. Yeah.
Yeah, this is the goal I want to achieve. Yeah. So right, when I actually prove the results, it does not matter too much. It will have a technical assumption, even though I don't think I will be able to cover under exactly what scenario that's going to hold, but maybe we can take that offline. All right. Okay, so all right, so that's the model, and thanks for the questions. I think maybe this model makes more sense to everyone now. And so a priori, it's not clear such a mechanism exists, right? Like if you think about it, you're only given one distribution and you want to have a mechanism that performs well for every possible distribution that's close to it. All right, so what we did in these two papers is to show that such a mechanism actually exists in fairly general settings. Okay, and so with this robustness theorems, what we can prove is now you only need to learn a distribution f hat, right? If you can learn distribution f hat using samples from f, then it's sufficient to learn an approximately optimal mechanism. So that's sort of the meta theorem that falls from these robustness results. All right, so that's the robustness result. Questions? Okay. All right. So now let me show you these two case studies. And so let me start with using robustness to prove learnability for simple and approximately optimal auctions. Okay. So as I mentioned earlier, in the multi-item setting, the optimal solution is hard to characterize. But even though we don't know the characterization, we do know that it needs to be quite complicated. Okay, so a recent trend in research has been focusing on designing simple mechanisms, usually of the form of posted price, and prove that these simple mechanisms have sometimes constant factor approximations. Okay, so this has been a long line of research. And so now it has been quite successful, and we now know that these type of simple mechanisms can get constant factor approximation in fairly general settings. The only assumption that you would need to make here is that you need to assume the items have independent values. Okay, so you need the item independence for these approximations to hold. And the current champion mechanism is by my student Mingfei Zhao and myself. So we call the sequential posted price with entry fee mechanism, and for sure I'll call it SPAM. So the exact description of the mechanism is not super important, and you would not need to understand the mechanism to understand this talk. So let me just describe the mechanism sort of intuitively for you. Okay, so it's a sequential mechanism. And so the bidders arrive in some order. And when a bidder arrives, I'm going to first ask the bidder to pay an entry fee. So the way to think about it is you're maybe dealing with Amazon Prime. So there's a membership fee. Okay, so you first need to pay the membership fee. Once you pay the membership fee, you can enter the mechanism. And then there's a price for each item. Now you can take whatever bundle you want by just paying the item prices. Okay. So that's roughly what this mechanism is. All right. This mechanism is known to give you a constant factor approximation in fairly general settings. Namely, the bidders have XOS valuations. The assumption is you need item independence. So I will not define what XOS is formally. It's a quite general family of valuations. It includes things like submodular. So, okay, so we know the simple mechanism gives you a constant factor approximation. And one might think that since this is a mechanism that with some nice structure, I can apply the pack learning approach to learn a good span, okay? But turns out that's not true. So if you want to learn a span, you would actually first need to establish its statistical complexity. And turns out even with just two bidders, spans have exponential statistical complexity. So that means if you go through this route, you will only get an exponential upper bound on the sample complexity for learning a span. Okay. So what we showed is that you can actually use this robustness approach to learn a span using only polynomial mini samples. Okay. So what I emphasize is that the sample complexity for learning a good span is polynomial. The reason that the pack learning approach gives you exponential is just some issue with that approach. And I'll discuss what that issue is. And our robustness-based approach is actually more flexible and powerful here, and it allows us to pin down a polynomial sample complexity. Okay. All right. So, so since I'm in the item independent setting, so let me be a bit more specific about the model here. There is some subtle difference. So since I'm in the independence case, so now for every bidder I and every item j, I have the marginal distribution of bidder i's value for item j. I'm going to denote that fij. So now I'm assuming for every such marginal, I'm giving an approximate distribution. So that's my fij hat. And the true world is that for each of these marginals, fij and fij hat are within Kolmogorov distance epsilon. Okay. So what is the Kolmogorov distance? That's just the biggest difference in the two CDFs. Okay. So you look at the CDF of f, the CDF of f hat. You look at the biggest difference. So I'm taking the soup over all values of x. So if the Kolmogorov distance is small, that's my assumption, then I can learn a span using only f hat such that its revenue with respect to the true distribution is a constant factor approximation of the optimal revenue with respect to the true distribution minus a small additive term. Okay, so again, m is the number of items, n is the number of bidders. And so here the approximation essentially matches the approximation I have in the previous slide. And using this robustness result, you can get a sample complexity. And I think for now, it's clear that all you need to do is to learn each marginal within Kolmogorov distance epsilon. All right, and how can you do that? So we're going to appeal to the amazing fact by these three guys, and usually known as the DKW inequality. So let me write down the inequality for you. It says that if you take n samples, capital N samples, and you look at the empirical distribution f hat, okay? So you will see that the true CDF and the empirical CDF are always within C over root n with very high probability, okay? So that's what the DKW inequality says. And I would like to, this is a very useful fact, and I would like to point out, why it's amazing. So if you're not having, you don't have the soup here, you just care about one particular point X, and you care about the CDF for that point, this is trivial. This follows from Chernoff bound, okay? The amazing fact here is that you can actually talk about the soup of X, that means you deal with all X simultaneously, and you still only need the same number of samples. Okay, so that's the DKW inequality. And using the DKW inequality, you can learn F hat within cohomograph distance quite easily. And the number of samples is just quadratic in the accuracy you want. Okay, so combining these two results, you will get sample complexity to learn a good span. Okay, all right, so but remember that I mentioned that using pack learning, you will get an exponential sample upper bound. Okay, but using this robustness result, somehow you can get a polynomial sample complexity. So what went wrong? Okay, what went wrong with the pack learning route?
Can I ask, can you go back here? Yeah. So one question, two questions actually. The first question is like here when you have this, this is a constraint we have seen in the previous page, right? So what you're trying to do is you maintain this. So this is given from beginning. This is a condition we want to do, and the next question is we design this. We design this mechanism. Do you mean?
Right. So okay. So like it has two parts, right?
Design this mechanism, maintain this condition, and achieve this approximation result, or what?
Right. So okay. So let me go back a bit. So, okay. Mm-hmm. So in the robustness part, your input is F hat. You only have F hat. You don't have anything else, just F hat, okay? Mm-hmm. Or F hat IJ for every IJ pair, okay? That's all you have. Mm-hmm. So what we show is that using F hat, I can design a mechanism M, okay? Such that it has the following guarantee, okay? What guarantee do I have? The guarantee is that for any true distribution, okay, if you don't want to talk about true distribution, that's fine. Okay, for any distribution F that satisfies this condition, that meaning their cohomograph distance for each pair is less equal than epsilon.
Right.
All right. So like I'm given F hat, but I prove to you for any F that's close to it, the following is true. The revenue of my mechanism with respect to F, which is this unknown distribution to me, is at least a constant factor of the optimal revenue of this unknown distribution minus this epsilon times m squared times n times h. Okay. That's what we prove.
Yeah, good.
Right. So that's what we prove. Yeah. And then combine this with the sample complexity. Yeah.
And the next equation, next formula going down. Yeah. So for this formula, so is it similar from with what we use for the like tracking model? Like they have like a square root of t in there or what?
So the square root of n is quite common. In fact, even you don't have the soup, you will have the square root of n showing up in Chernoff bound.
Right.
So
like a square root of n, 1 over square root of n is something like the deviation. Oh.
Yes, that's the standard deviation of Gaussian. And yeah, so like, for example, even just estimate one number with an additive error of epsilon, you need 1 over epsilon square samples. That's essentially the same as this root n thing here. Okay. So what I'm pointing out here, the impressive part of this theorem is that it says for the soup of X. So you're simultaneously talking about the CDF at every point, and you can prove they're still close, only using n samples. So that's much stronger than just talking about, say, for 1 point, the 2 CDFs are close, which just follows from the Chernoff bound.
Thank you. Thank you.
Yeah, right. So that's the DKW inequality, and you can combine that with our result to get the polynomial sample complexity. All right, so let me just quickly point out, what allows us to establish this polynomial sample complexity while the pack learning approach failed. Okay, so in the pack learning approach, so any bound that uses the statistical complexity will actually work for arbitrary distribution. Okay. And that basically forces these bounds to be very pessimistic, and sometimes too pessimistic if you're dealing with special distributions. And we are dealing with special distributions. Remember that I'm making the assumption that items are independent, right? That's, after all, what you need for the approximation result to hold, right? If you don't have item independence, why do you talk about these simple mechanisms? You don't have any approximation guarantee. Okay, so if you want to use this sort of statistical complexity, like, they're just too pessimistic for these special distributions. In our case, the product measure. But what we managed to do is we use robustness, and this robustness is more flexible and allows us to capitalize on the special properties of the product measure. Okay, I don't have time to go, so I prepared one example to show that why our approach is more flexible, but I won't have time to go into that. Let me just very quickly show you the thing that allows us to actually beat the statistical complexity. So basically what we did is we showed that if you want to prove robustness for a span, all you need to do is to prove robustness for indicator functions for sets that we call our single intersecting. Okay, so that's a generalization of convex sets. So what is the definition for single intersecting sets? It's quite simple. So you just draw any axis parallel line, okay? And you look at the intersection of that line with your set, okay? If the intersection is a single interval always for any axis parallel line, your set is single intersecting, okay? So for example, if you look at this blue set, it is single intersecting, right? No matter how you draw the axis parallel line to it, you will, the intersections are most a single interval. But the red one is not, right? If you draw this green line, you actually have two intervals in the intersection. And clearly any convex set is single intersecting, right? So what we managed to prove is for single intersecting sets, you actually have robustness. All right, and that's, okay, so it's summarized in this lemma. I won't have time to go into exactly what that lemma talks about, but I want to point out that this lemma gives you a corollary that's about uniform convergence for learning this single intersecting sets. It says you can attain uniform convergence for learning single intersecting sets using only k squared over epsilon squared samples. K is the dimension of the space you're in. If you use VC dimension, you will actually see that these sets are not learnable at all. You will only get an infinite upper bound because the VC dimension is in fact infinite for these sets. Okay, for many of you who know VC dimension, that even if you're just looking at convex sets, the VC dimension has something to do with number of facets in your convex set. And that number, the number of facets, can easily go to infinite, so you actually don't have any sample complexity flowing from VC dimension. Okay, so I think maybe I have another 10 minutes or so. So let me quickly tell you another case we apply this modular approach that allows us to go beyond the item independence assumption. Okay, so that's recent work. Okay, so here I'm changing the robustness model a little bit. So now I want to deal with dependent items. So now for every bidder, since the items are not independent, the distribution for this particular bidder is going to be a joint distribution across all the items. Okay, so we also change the model accordingly. So we say that we know an approximate joint value distribution Fi hat. And again, I assume Fi and F hat are close in some statistical distance. And I want to design a mechanism M based on only F hat so that its revenue is, now I don't have this constant factor here. So I want the revenue for M to be almost as good as the true optimal revenue for F, only subtracting a small additive term. Okay, so it's a strengthened version of the robustness model. So, okay, this is even more unlikely to exist. But what we show is that you can still construct such a mechanism if you allow approximate truthfulness. So if you allow M to be approximately Bayesian incentive compatible for the true distribution, then you can actually have such a mechanism M. Okay, and this allows, this robustness model allows you to have arbitrary dependency between the items because I'm only talking about joint value distribution. Okay. And so let me say a few words about the particular, like the most interesting statistical distance we study in this paper. So the most interesting one, in my opinion, is the Prokhorov distance we study. So it's a very liberal metric. It's sort of the standard metric used in robust statistical decision theory. So when I say two distributions are close in Prokhorov distance, intuitively it means the following. Okay, suppose F is the true distribution, F hat is the approximate one. If they're close, that means two types of error could creep in when you generate F hat. Okay, so the first type of error is that with a large probability, you misperceive the value by a small margin. Okay, but that's kind of common. Like just imagine maybe you're rounding all the values up to a certain big complexity. Okay, so you have some small error, and also it allows the type of error that with a small probability, you misperceive the value by a large margin. Okay. It does not allow with large probability, you misperceive the value by a large margin. Okay. So if you have that type of error, you're not close in Prokhorov distance. Okay. So as I mentioned, this is a very liberal metric. So in fact, if you're close in many of the familiar statistical distance, like the total variation distance, the Hallinger distance, the chi-square distance, you're also close in the Prokhorov distance. Okay. So, and if you have a more liberal metric, it's just harder to prove robustness result because you need to deal with more possible true distributions. Okay. All right, so this has been studied in the literature, but by Bergman and Schlag, they only look at the case where there's only one bidder and one item. So here we're dealing with multiple items, multiple bidders. Okay. All right, so what is the robustness result we establish? So we actually also consider single item case as well. Because now I want to actually get a robustness result that gives almost optimal revenue. So in the single item case, we look at the Kolmogorov distance and Levy distance. So Levy distance is essentially the same as Prokhorov distance. So in the single item case, we show that you get almost the optimal revenue minus n times epsilon times h. N is the number of bidders. Okay, so this will give you already a quite good sample complexity, but not optimal. And the mechanism is IR and dominant strategy incentive compatible. Okay, so that's for the single item setting. Okay. For multi-item settings, you also get up to quite close to the real optimal. It's just the optimal minus some small additive term that decreases if you drop epsilon. But the main difference between multi-item setting and single item setting is that here we're not getting exact truthfulness. We're only getting approximate Bayesian incentive compatible. In fact, we're getting, so the truthfulness also, okay, I get better truthfulness if I have a smaller epsilon. But how truthful it is depends on how big this epsilon is, okay? But if you really think about this setting, this is kind of natural because the Bayesian incentive compatible concept depends on the distribution. Since you only have an approximate distribution, it's a bit hard to imagine you can design a mechanism that's actually Bayesian center compatible for an unknown distribution. Okay, but okay, so like what we get is you get approximately truthfulness and up to epsilon optimality. That holds for both total variation distance and Prohoff distance. Okay, and an interesting byproduct we get from this robustness result is you can also prove the optimal revenue is in fact continuous in terms of this statistical distance. So that means if you get a distribution f hat and distribution f, these two distributions are close in one of these statistical distance, then the optimal revenue is also close. Okay, so that's I think interesting byproduct of the robustness result. All right, so I think I have maybe 3-4 more minutes. Let me just quickly say how you can apply this robustness result to learn auctions when the items are dependent. Okay, so turns out when you deal with dependent items, it's a bit more subtle. And you first need to think about how you model dependency. And the reason is that if you just think about arbitrary dependence, we already know that that would require exponential many samples. So there is a lower bound that says if you have arbitrarily correlated items, you need exponential many samples to even just get a constant factor approximation. Here I'm trying to get something that's almost optimal. So you will also have this exponential sample complexity kick in. Okay, so but one thing to notice is the example in this paper by Dugmi et al. They actually require very strong dependency to construct that example. So the hope we have here is that maybe you can have a parameterized sample complexity that degrades gracefully with the degree of dependence. Okay, if you have more dependence, I'll have worse sample complexity, but if I have less dependence, I actually have good sample complexity. Okay, so the way we try to model this is we use two of the most prominent graphical models, namely Bayesian networks and Markov random fields to capture this dependency structure. I want to point out like these graphical models are fully general. So if you allow the graphs that these models should define on to be sufficiently dense, they can capture arbitrary dependence. And the natural parameters that models the dependency, the degree of dependency is the maximum size of a hypergraph in an MRF and the largest in degree in a BaseNet. So yeah, let me skip the latent variable part. Okay, and let me just quickly tell you what's a BaseNet, what's an MRF. So a BaseNet is captured by a directed acyclic graph. And here you can imagine that I have 4 items that I'm selling, and their values depend on the state of my residence. Okay, so clearly the values of these 4 items are dependent. Okay, in fact, even if I say condition on my value for umbrella and sunglasses, my value for skis and surfboard will still be correlated. Okay, but they will be independent once I fix the state of residence. Okay, so the dependence between these values are all go through the state of residence. Okay, so that's a way to model particular type of dependency in the item values. Okay, so that's the BaseNet. In MRF, again, is defined on a graph, and every node is a random variable, and there's an edge between them, meaning that there is some dependency between them. And the degree of dependency is captured by something called potential function on every edge. So that's the MRF model. And what we show is that in MRF and BaseNet, you can always learn within Prokhorov distance epsilon using a small sample complexity. So the exact number does not matter. What I want to point out is it is polynomial in everything about my model and only exponential in the degree of dependency. Okay, so if you have small dependency, you have polynomial. If you have large dependency, the sample complexity has to grow fast. All right, so using that, you can get sample complexity. It recovers the result by Gonczewski and Weinberg and allows you to also prove learnability for auctions when the values are captured by MRF or basis. Okay. So I'm running out of time, so let me skip all this proof vignettes. And let me just show you the last slide. All right.
Okay. Thank you. I think we have time for one quick question. Any question from the audience? Okay, maybe I want to ask you a question because the students can ask you a question in another meeting room. Sure. So in the beginning of the talk, you mentioned the challenge of like choosing the right class of mechanisms to learn optimal one from that. So that is in the PAC learning model. So in your model, you just like try to get the approximately optimal one directly in the robustness part. Do you have that? You don't have that challenge? Is that correct?
That's correct. So in the PAC learning model, you have to pick this class of mechanism upfront, right? So in my case, of course, you will still need to design the mechanism, but I'm not restricting my mechanism to be, have small statistical sample complexity or anything like that. I only need to make sure it's robust, right? But like, I don't have any restriction in, how I pick the mechanism. As long as you can prove it's robust, it's fine. So that's why I said, like, this is just about mechanism design. You don't need to worry about statistical complexity.
I see, but you may sacrifice the truthfulness a little bit.
Right. So in the case when I need to go to this up to epsilon optimality, I need to sacrifice the truthfulness a little bit. And in fact, one of the open questions I want to ask is whether that's necessary. Maybe you don't need to sacrifice the truthfulness.
I see. Okay, thanks. Okay, I think, so let's thank Cai Yang for this great talk. I think the next talk gonna start soon. And okay, fine. I think this session ends.